Alright, so if you were comfortable with yesterday's stuff, it's time to get uncomfortable. Alright, we are talking about Le Chatelier's principle. Okay, yes, that is how you say it. So basically, what the purpose of his principle is that we are going to balance out any change that happens once we get to equilibrium. So it says if a chemical reaction at equilibrium is subjected to some kind of change in conditions that displaces it from equilibrium, then the reaction proceeds towards a new equilibrium state in the direction that offsets the change in conditions. Okay, so we're at equilibrium, something happens, we're not in equilibrium anymore, but we're shifting towards a new equilibrium. Okay, so we've got three factors that can affect a reaction at equilibrium. The first one is concentration of a reactant or product. Okay, it says when a system at equilibrium, when a system is at equilibrium, increasing the concentration of a reactant or product will cause the reaction to establish equilibrium by shifting the reaction in a direction which relieves the stress. So, here we have this reaction. So if I were, let's zoom in here, if I were to, oh gosh, if I add A2 to this reaction, so I'm increasing the concentration of A2. Alright, so if that happens, my A2 is on the left side of the reaction. So if I add more A2, I'm increasing the amount of A2 on the left side. So that means to make the amount of A2 go down, the reaction has to, ooh, that's ugly, shift right, okay, towards the products. So it's going to make more product to counteract that increase in A2. I also want you to make a note that typically water has no effect, usually. Okay, so here it's just kind of going through a few more scenarios. When the reaction's at equilibrium, the concentration of B2 is increased, the reaction proceeds from left to right to relieve the stress. Okay, so again, that's all really Le Chatelier's is. There's some kind of stressor added, and we're trying to counteract that stressor or stress. So if I did add more AB, if that concentration increases, then my reaction is going to shift to the left to counteract the AB that's increased. All right, another factor that can change or affect a reaction at equilibrium is volume or pressure. Okay, so this is for gases only. Okay, they've given us an example of an equation. It's got all gases. Okay, so something that happens here or that you need to make note of. Okay, if, let's zoom in a little bit more. If the volume goes up, the pressure goes down. Okay, we learned that last year in pre-AP Chem with Boyle's law. So the P1V1 equals P2V2. So it's going to shift to the side with more moles of gas. Okay, so if in this situation for this particular reaction, the volume went up, okay, that means my pressure goes down. So which side of the reaction has more moles of gas? Okay, that's going to be the right side because I've got 2 moles of gas on the right side, 1 mole of gas on the left. So my reaction is going to shift to the side with more moles to increase the pressure. Okay, because over here, let's kind of write this out. Again, I've got 1 mole, which is a low pressure. That's a P. Over here, I've got 2 moles, okay, which is a high pressure, okay, because I got more molecules bouncing around, hitting each other, all that good stuff. Okay, so then the opposite, so if the volume went down, pressure would go up. And so I'm going to shift left, okay, to the side with less moles to counteract that pressure increase. Okay, so basically this paragraph says what I've said up here. Just depends on what's happening with the volume and pressure, and then you've got to pay attention to the moles of gas and how that would play into the increase or decrease in pressure. Okay, the third factor that affects a reaction at equilibrium is temperature. Okay, to understand how temperature affects a reaction at equilibrium, we have to consider this equation. Okay, so it did say here that this reaction is endothermic. Okay, endothermic means that heat is a reactant. Okay, in an exothermic reaction, I'm giving off heat, so heat's a product. So it's the opposite for an endothermic. Okay, so that's why I've got this heat here. All right, so we should probably make a note of this too. So delta H for this reaction is going to be positive, okay, because they just told us it was endothermic, so it's taking that heat in. Delta H is negative for an exothermic reaction because it's giving it off, so you're losing heat. And like I mentioned a second ago, heat is the product. All right, so let's go through a couple scenarios. So if I were to add heat to this reaction, my reaction would shift right to get rid of the heat or to counteract the heat. And then if I were to take away heat, it would shift left to make more heat, okay, or to heat back up. So one thing I do want you to pay attention to that it says in general for endothermic reactions, decreasing the temperature shifts the equilibrium towards the left. Adding heat shifts it to the right, so kind of just what I was just saying. So it's just the opposite for exothermic reactions. Okay, so here's our next reaction. Let's pay attention to what we have here. So if you notice, I got me a liquid. And let's see, some of it's on the next page, but I'll kind of tell you. So it does say that the delta H is negative 1036 joules or kilojoules. Okay, so if it's a negative delta H, that means that I am exothermic, which means I have heat as a product. Okay, let's also pay attention to how many moles of gas we have. So over on the left side, I have 5 moles of gas, and on the right side, I have 2 moles of gas. Okay, so let's go to the next page and see what questions they ask. All right, so it wants to know the amount of, or what would happen if the amount of water is increased. Okay, water in that equation is a liquid. Okay, and liquids and solids have no effect. on equilibrium. Okay, and they don't have any effect on equilibrium because they're not in the equilibrium expression. So when we write that K equals products over reactants, we never include liquids or solids. Oh wait, in equilibrium expressions. All right, it wants to know the temperature of the reaction is increased. What way am I going to shift? So that was an exothermic reaction. So if I increase the temperature, that means I'm increasing the heat, which is on the right side. So that means I'm going to shift left. Okay, next one. They will want to know what way it's going to shift if the volume is decreased. So if I decrease the volume, that means I increase the pressure. Okay, and we want the pressure to go down, so we're going to shift to the side with less moles of gas. Okay, so remember I had 5 on the left and I've got 2 on the right, so I'm going to shift right. All right, this last one, the amount of H2S is decreased. Okay, H2S is on the reactant side. So if I decrease that amount, I'm going to shift to the left to increase that amount. Awesome. Okay, and then I did want to talk about something really quick. I want to do a little bit of an example. So with concentration. Okay, so concentration factor example. Okay, so again, these are factors that affect equilibrium. All right, so say I had silver plus hydroxide, okay, yielding silver hydroxide as a solid. All right, so let's just go through, I just want to go through a few scenarios. So if I added chlorine to this, okay, one thing that could happen is I could make silver chloride, okay, because silver plus 1 will bond with chlorine minus 1. So if that happened, it would be like I was removing silver. So if I'm removing silver from that equation, that means my reaction is going to shift left to counteract that decrease. Okay, then if I added hydrogen, okay, technically, remember this is an acid, even alone. Okay, what could happen here is this H plus could bond with that OH. Okay, so it could make water. Okay, and if I did that, it would be like I would be taking away that hydroxide because I'm making water. So I'm taking the hydroxide out of the equation, so my reaction is going to shift left to counteract that balance. So if you were to add something that's not there, it can have no effect, but it also could have an effect. It just depends on what you're adding and how it's going to play into those products and reactants. All right, so now let's talk about Q. Okay, so Q is the non-equilibrium reaction quotient. So basically, Q is a fake K, like a wannabe K. Like, remember, K is equilibrium. And Q only deals with initial concentration. Okay, because it's not at equilibrium. Okay, so because remember, we were at equilibrium, something happened, so we're no longer at equilibrium and we're trying to get back to it. So Q wants to be like K, okay, but we're not at equilibrium. So Q is basically dealing with that middle ground. So where we were at equilibrium, we're not anymore, and we're trying to get back to it. Q, we write, or we solve for it the same way. Okay, so products over reactants. And let's write that down actually. Product over reactant, still dealing with concentrations. Okay, and we have this little table. You do not have to memorize this. Okay, I'm going to show you how to kind of rationale your way through it. So it just kind of takes Q, it compares it to the K that you'll find, and it'll tell you what will happen. So it's going to tell you what's going to happen to Q. So let's just go ahead and jump in and do an example. I'm going to write this on the next page because that kind of makes me mad. Alright, so I'm going to rewrite this equation. And, here we go. NOBR. It's a gas. NO plus 1/2 Br2 gas. Alright, so I got all gases. That's nice. Alright, so using this reaction, it's been carefully studied at 350 degrees Celsius, and Kc is 0.079. Which direction will the reaction proceed to establish equilibrium under the following conditions? Okay, so here I've got the initial concentration of NOBR as 0.1, and then it's saying I don't have any nitrogen monoxide or bromine. Okay, so that means I'm going to want to shift to the right so that I do have a concentration of this. Okay, so I'm going to shift right to counteract that there's no concentration, or that there's, so that I can have it. Alright, situation number 2, I have no NOBR initially, and then I have nitrogen monoxide, and I have bromine. Okay, so I've got a concentration of my products. I don't have any reactants, so that means I'm going to shift left. So I can do a rice table to figure out the scenario 1 and scenario 2. You don't have to, because I wouldn't have any numbers really to put in it except zeros and these 0.1s for the concentration. But here on this next one, because remember when we talked about with K2, I always shift towards my zeros. Okay, so if my zeros are on the product side, I'm shifting towards the products. If my zeros are on the reactants side, I'm shifting towards my reactants. Okay, so this next one, I don't have any zeros, so that's a problem. Okay, so what I'm going to do is I'm going to do a rice table to try and figure out what way I'm shifting. Alright, so I'm going to rewrite this reaction. So I've got NOBR, double arrow, NO plus 1/2 Br2. Alright, I do know my initial concentrations because they told me. Everything is the same. Okay, so I don't have any zeros. That's a problem because I usually shift towards my zeros. Okay, but what I can do is I can go ahead and I can solve for Q, because remember Q deals with initial concentrations, and that's all I have. Okay, so I'm going to be doing products over reactants. I do need to write an expression for Q, so actually wait, Br2, okay, to the 1/2, and O to the nothing, and then NOBR on the bottom. Plug in my numbers. Okay, so I got 0.1 to the 1/2, 0.1, 0.1. Okay, so Q is 0.316. Okay, and I can figure out what's going to happen just by comparing it to that original K that I had. Okay, because remember, I can tell which way Q is going to shift because I figured out Q for the initial concentration, and I can figure out which way Q is going to go to be like K. So here I've got Q is greater than K, okay, because I've got 0.3 versus 0.079. So you can think about it a couple ways. So again, keep in mind Q wants to be like K. So I know that Q is products over reactants. So for Q to be smaller, I've got to add more reactant, okay, because my reactants are on the bottom. Okay, because Q is going to want to go down because right now it's bigger than K. So it wants to be like K. I'm going to try and go down, so I would add more reactants. So you can figure it out that way, or you can go back to basic math. Okay, so I know that Q is currently bigger than K. Okay, so in order for Q to be like K, I'm going to shift to the left, which is towards my reactants. Okay, so you can do it like that. Whatever you feel most comfortable with, you can figure it out like a reactants or like a fraction, or you can do the number line. But this is so you don't have to memorize that table. I told you I wasn't going to make you memorize it. You just need to be able to rationale your way through things. Okay, so the last part over here was I've got a 0.2, 0.05, and 0.1 concentration. So I can go ahead and write that all out. I'm just going to do the R and the I from rice. So I had 0.2 here, 0.05, and 0.1. I'm just going to go ahead and write it. So Q equals 0.05, 0.1 to the 1/2, 0.2. Okay, that equals 0.079. Let's go. Okay, so Q equals K, which means there's no shift. Yay. Sweet. All right, moving on. 3 more problems. Actually, you know what? We're not going to worry about this one. Okay, they put that on the test one time. I don't think it'll happen again. All right. All right, so it says that my Kc for the reaction is 19.9. All right, it wants you to find the equilibrium concentrations of all species if the initial concentrations are given to you this way. Okay, so the first thing we need to do is find Q. All right, I don't have any zeros, so I'm not really knowing what way it's shifting yet. Okay, so I'm going to do a rice table to figure out which way it's shifting. Cl2 plus F2 yields 2ClF. Okay, I've got my initial concentrations. They gave those to me in the problem. And okay, I need to do the change. Okay, so I'm going to do x, 2x. I don't know what way it's shifting yet. That's what I got to figure out. So this is 0.4 plus x, 0.2 plus x, and 7.3 minus 2x. Okay, so let's figure out which way it's shifting real quick. So Q, I'm going to do products over reactants. Okay, so that's 0.4. Ooh, that was ugly. 0.2. Okay, when I get that, my Q, oh my gosh, 666. Yikes. So Q right now is greater than K because K was 19.9. So again, however you want to do it, number line or not, if I want Q to go down to be closer to K, I'm going to have to shift left. Okay, so that means I'm coming back in here and I'm adding these plus signs so that it shifts left. Okay, so that justifies me doing those signs here. And we're not going to do the math for this because you will not see any math like this on the AP exam. Because technically what you should do is set up an equilibrium expression. You know K, because K is 19.9. Oh gosh, boop. So you got this 19.9, and then we don't have a value for x. So you have to plug each one of these into the equilibrium expression, and that's too much. Okay, we don't have to do that on the AP exam, so we're not doing it in class. What's a plus? Okay, so your x is 0.93, and then just like we did yesterday, you take that x, come back in, plug it in for those guys to figure out your equilibrium concentrations. Okay, next one. Last one. Let's go. All right, so K for the decomposition of ammonium hydrogen sulfide is this 1.8 times 10 to the negative fourth at 298 Kelvin. Let's double check our reaction. I do have a solid in there. Okay, remember solids and liquids have no effect on equilibrium, so we don't even care about it. So I'm going to do a rice table because I do not know any of my concentrations. Okay, but I do know K. So I got to use a rice table because I don't know everything. Alright, so rice. Okay, I'm going to rewrite my reaction. So NH4HS, double arrow, NH3 plus H2S. Okay, so I had someone ask me yesterday, what do we do when we get a solid? What do we do with the rice table? Okay, this is so awesome when you get a solid because look what I get to do. Boom, boom. None of that even matters for that compound, okay, because it's a solid. All right, so I did not have any initial concentration of these two because if I did, it would have told me. I always shift towards my zeros, so I don't have to find a Q and compare it because I have zeros and I always shift towards those. So plus x, then I have x here and x here because I'm basically adding them. Okay, and then let's write our expression. So K is equal to products over reactants. So I have my NH3 and my H2S. Okay, technically it would be over 1 because I do not include the solid in there, but I can just leave it like this. So that means I have 1.8, because this is my K, 1.8 times 10 to the negative fourth equals, and we can just call this x squared, okay, because I had no coefficients from the problem. So I've got two x's, x times x is x squared. So then my x, because these are just x's over here, so x is equal to the concentration of ammonia, which is equal to the concentration of dihydrogen sulfide, which is equal to 0.013, that is so ugly, 13 moles per liter, okay, because it's concentration. All right, and that's it.